Hello, everyone. Welcome to another wonderful day of chemistry. So today we're going to be talking about concentration cells, which are just a fancy version of galvanic cells. So as we've seen previously, we can go ahead and control the amount of energy an electrochemical cell produces by changing the potential of the chemical reaction. And we've also seen that you can change the potential of a reaction simply by changing the concentrations of products and reactants. So today we're going to be bringing these two together. So one of the cool things you can do is you can set up electrochemical cells where you have a different concentration of ions in your anode as in your cathode. And as a result, you can change the overall potential of the system by changing essentially this ratio of products and reactants. However, a very cool variant of this is what happens if our anode and cathode reaction are the exact same reaction. Also, the one we're going to look into today is going to be the reduction of hydrogen. So our anode will be the oxidation of hydrogen to form protons and electrons. And then over in the other cell, we're going to take those same protons and those same electrons and recombine them to make hydrogen. So at this point, it doesn't feel like this is a good energy storage mechanism or transfer mechanism because we have the same exact reactions. And so we can go ahead and pair these together to make kind of one of the weirder reactions you've ever seen. Hydrogen plus protons makes hydrogen plus protons. And this is one of the reasons why I often emphasize these notations, specifying the exact phases, and now becomes very important, the exact locations. Because what we're doing is we're taking hydrogen in the anode and breaking it down to protons. And we're taking protons in the cathode and recombining them to make hydrogen. So really what we're doing is we're moving hydrogen from the anode to the cathode and protons from the cathode to the anode. And so as a result, really what we're doing is we're moving things either with or against a concentration gradient, which, as we saw during osmosis, can be quite an important feature. So one of the fun bits about this reaction is the standard state cell potential for this reaction, and really any of these concentration cells will be 0 volts, because no matter what my reduction potential is for this reaction, it will be cathode minus anode. And if they're the same number, our cell potential will always be 0. And as a result, it turns out the potential only depend upon this Q, this ratio of products to reactant concentrations. So in this case, we're going to be taking the square of the proton concentration in the anode times the pressure of hydrogen in the cathode, and then dividing it by the square of the hydrogen concentration in the cathode times the pressure of hydrogen in the anode. So again, you'll note that the species are the same on top as on bottom. Only big difference is going to be the location: cathode, anode, anode, cathode. Protons are effectively moving this way, while the hydrogen gas is moving this way. It's very easy to mess up the signs on these. And again, it is worth noting that while the nature of the reaction will not change the standard state potential, it will control the number of electrons being transferred in this case too, and it will change what products and reactants are present. However, in a reaction like this, it's very natural to have the same exact pressure of any gases the same in both cells. You can imagine enclosing this whole system in an ambient pressure system, at which point the reaction really can be simplified to moving hydrogen from the cathode to the anode. And this does feel a little bit awkward in some of the cell notations, because again, it feels like we should be moving from reactants to products. And this is one of the reasons why it's very important to carefully write out your reaction so you know exactly what species are present on which sides of the reaction. But we can end up reducing the whole potential of this system to our consonant soup, RT over NF, and then the natural log of the ratios of, again, the square of the proton concentration in the anode over the cathode. So let's go ahead and take a look at this for a real system. So what would be the cell potential, again, at room temperature, if I have an anodic pH of 10, so I've got a pH 10 here, and the cathode has a pH of 2. So this means we have a high concentration of protons in the cathode, low concentration of the anode of protons in the anode. So this should end up being a favorable reaction. And let's take a look at it when we do the math. So one of the notable things is protons can essentially be given as 10 to the negative pH. So this means in the anode, we have a proton concentration of 10 to the negative 10th, and in the cathode, 10 to the negative 2. Now let's go ahead and plug that into our Nernst equation. We can, since we're at room temperature, we can go ahead and consolidate our RT over F into 0.0257. I did drop a negative sign here. N is 2. And again, products over reactants will end up canceling the negative sign here. And it turns out with a potential of 0.47 volts. That's actually a fair bit of energy. If you remember back to last time, this is about 1/5 of what you would get out of a battery just by using the concentrations. And so one of the things that is very worth noting is you can drive a lot of very cool chemical processes just by reducing the concentrations of the products, in this case, the pH at the number of protons at the anode, and increasing the concentration of the reactants, in this case, the concentration of protons on the cathode. And using these concentrations alone, a large potential can be generated, which can drive a fair bit of electricity transfer. And it's worth noting that this isn't just something we do as people trying to find ways to store energy. Turns out this is one of the biggest energy storage mechanisms by biology. So a lot of biological cells use this uneven distribution of ions as an energy storage mechanism and as a way to build up electronic charges. So it's worth noting, this is one of the ways that metabolism works, is that it builds up a proton concentration where mitochondria tend to raise the pH inside of the mitochondria. So again, low hydrogen concentrations. And that way, when protons move the other way, you can use this to drive a lot of cool processes like making ATP. It's also worth noting a lot of neuronic synaptic connections, which are essentially electrical charges, are built up by essentially having large biases of sodium and potassium. That way, what you can have is that movement of potassium and sodium can help release a fair bit of potential charges. So again, just by playing with the concentration of a system and having no actual chemical reaction, you can release a fair bit of chemical energy. So next time, we're going to go ahead and take a look at the other way. By measuring a potential, can I go ahead and get a good idea of what the concentrations of various ions are? As next time, we look at ion sensing electrodes. Until then, take care.